The following audio recording has been designed for learning purposes only. Do not share, distribute, or provide any type of copies, or this audio lesson will not be made available to you. Good luck with today's lesson.
Alright, so when we we usually titrate the acid with the base. So the acid is in the beaker, and the base is in the burette, like we did in the lab. And so what we should expect in general so the acid is in solution, so it's going to start out at a low pH because there's only the acid present, and then it's going to rise up really steeply and then head out. So that's kind of an integral sign look to it. And this is the inflection point. And then halfway up that inflection point is what we call the equivalence point. And if we go back here, this is the pH at equivalence point. It's also called the end point. Technically, there's a little bit of a difference between them, but for what we do, we can call them the same thing. So that's for titrating an acid in the base, but there's a little bit more to it. It depends on the strength of the acid in the base we're using. So if we did a strong acid titrated with a strong base, we'd expect that the pH would be very low to start because it's the strong acid, and then it shifts up and goes very high, and the equivalence point is going to be exactly 7. So an example of this would be HCl plus NaOH goes to NaCl plus water. And that's where we said that this salt comes from a strong acid and strong base, and the pH is 7 because of it, because they cancel each other out. So when they make this salt, nothing further happens. This does not hydrolyze. Neither of those can do anything. If we take a strong acid and titrated with a weak base, well, at the end point, all that's left is the base. So we expect for a strong base to be really high up. But the weak base, the pH just won't go as high. So the start is low, but it's going to top out at a lower level. And so this, and I should say this makes this 7. It would be 7. So the equivalence point is going to be less than 7. Because that strong acid and the weak base are going to make a salt that has those parents, and we said that when that happens, the pH is going to be less than 7. How much, we don't know. We have to do the calculation. But we definitely know that that is the case. So an example would be HCl and ammonia, and that would make ammonium chloride. And the ammonium chloride hydrolyzes with the water, and it does this. And that's why it's acidic, because it produces H3O+. Sodium chloride in the strong acid, strong base case doesn't do anything. All right, and then the last one that's easy to deal with is a weak acid and titrated with a strong base. So I have to say titrated with, I keep trying to write weak acid and strong base, but I have to say which one was titrated with which. Well, I'll show you why. So if a weak acid is thrown in here, then its pH is going to start out higher than a strong base, assuming you have about the same concentration. But then the strong base is going to top out about the same as over there. So when we look at the equivalence point, pH at equivalence point is going to be greater than 7. So you should be able to say, you can see all the titration curves look essentially the same, but the difference is where their equivalence point is. So you should be able to say that. So if I say, just in general, so here's a weak HCN plus ammonia, or I'm sorry, let's say KOH. We'll use KCN. And then the potassium in the salt does nothing, but the CN minus will hydrolyze. And the CN minus plus water, it'll steal away an H plus. It'll make itself into the weak acid again and leave behind OH minus, which makes it basic. So we talked about the salts already, but now we're seeing the reaction that creates the salts. So from the titration curve, and that's what we'll do, well, not next, next week we'll do, you're going to do essentially the same stuff you did in the lab on Monday, but you're going to use a pH meter instead of indicator. So you're going to watch the pH, and you're going to be able to map out by volume. I should also put that in here. You're going to be able to map out by volume the pH. You're just going to add in 1 ml at a time, let it stir up, and the pH meter is going to tell you where you are. And it's going to just, when you do the strong acid, strong base, it'll just map this right out. Okay, and then the weak acid and weak base one is going to either shift below or above depending on the Ka and Kb. So we won't worry about that one. But you should know this qualitatively. You should be able to tell me what's the pH at the equivalence point for any of these three. Okay. So that's just qualitative. Now for the acid-base stuff, there's calculations based off of all three of these. But for the exam, you're going to have to do the calculation for that one. That's what you'll have to calculate. So on the homework, they might have you do the other ones. They work the same way, but just to let you know that this is the problem I'm going to do in class, and that's the type that you'll have. There'll be a different weak acid, probably the one that I use, different Ka, but the math will be the same. Okay. Oh yeah, and then just to show, we did the strong base with titrated with a strong acid. Okay, so if here the base is in the beaker and you added the strong acid, what do you think that curve would look like compared to this one? So here we have the acid in the beaker. This is in the burette. We're adding in the base. Here we have the base, and so you imagine we have the pH meter in the base. We're adding the strong acid. Where should the pH start on here? Should it be low or should it be high? High. And in fact, what you'd see, I'll do my best is you would get the mirror image. But pH is still going to be 7. So if you, on a standardized exam when they do this, sometimes students have sent me that practice one, and the curve is backwards. As you know, that's how they say it. So yeah, it is backwards. We don't normally, you don't normally titrate a base with an acid. You can, there's no problem with it, but the reason we do acids and to base is because it's just so you can get used to that curve. But you can see all the information is still there. When you get done, I mean, this is going to be lower than that. It should, if you did both of these, and you had the same concentrations, you should be able to take this one, like on a thin sheet of paper, flip it over, and hold it up to the light, and they should look exactly the same. They're just mirror images. So if you see that, Don't let that throw you. It won't be on our exam. We're going to definitely stick with just the acid being titrated by the base, whatever the base is. But same information can be gained. Okay. So let's do that calculation. Let me see what we got here. So I might ask you to draw a titration curve, and you just have to, for the answer key here, I give all the pH. Really, I just have to show that it's pH 7 for this one, less than for the strong acid, weak base, and then greater than pH 7 for weak acid and strong base. Okay, so let's do out. Now this type of calculation can get wildly out of control. There's going to be so much that we do. What I'm going to ask for is for you to tell me what the pH at the equivalence point is. But I could also ask, I won't do this on the exam, but you could certainly determine what the pH is here. From the time you enter some of the base, from here to here, this is a buffer. So what you do is you figure out the concentrations, that how much of the acid has been used up, how much conjugate base has been produced, figure out the concentrations, find the pH based off of the Henderson-Hasselbalch equation. And then afterwards here, this is only the base, so you figure out what the concentration is and you find the pH from that. But I'm not going to ask that. There's all kinds of stuff you can do here. What I'm going to ask for is this point. That's plenty. That's plenty to do. So with all the other calculations we have. So this is what I'm going to ask. It's going to look very much like this. What is the pH at equivalence point when 20 mils of, let's see, 0.8 molar. It's going to be on there. Let's see. We'll do that. HCN is titrated with 0.5 molar NaOH. Okay, and so we're going to need the Ka for HCN is 4.90 times 10 to the minus 10. Let's get this gone. All right, so here's the reaction. Here's what we're after. Is the HCN reacts with the sodium hydroxide. And it's going to produce sodium cyanide, which is a salt and water. Before the equivalence point, there's always some of this left over. After the equivalence point, there's some of this left over. At the equivalence point, both of these are gone. It's 100% this. That's a salt. So if that you put that, let's say I just said that, what is the what is the pH of this? Is it 7, greater than, or less than 7, based off of the parents? Strong base, weak acid. What's that? Yeah, because the strong one wins out. So you should know that qualitatively. That's a problem on the exam itself. But here, we're going to figure out what the pH is. The only reason I'm bringing this up is that you should be looking for a pH greater than 7. If you end up with pH less than 7, you probably found POH or something else went wrong. So it's always good to know where we're heading. But we're going to find out the exact pH based off of these concentrations and that Ka. Okay, so this is going to be greater than 7. All right, so, and we know that this breaks up into sodium ion and cyanide ion. Okay, let's say you forgot which one hydrolyzes. You shouldn't, because it's sodium. Sodium is a spectator ion. How do you know that this is the one that is going to be the one that hydrolyzes the water? Not based on any chemical theory, yeah.
It's a conjugate base.
Yeah, but and it's trying to get back to the weak acid, which you should know. But if you weren't sure, you're not sure how do you know that this is the guy that you want to be working with? What's the Ka for? Now I'll say it right in the problem. I said it for HCN, so you know that's the guy. So as an aside, I mean that's the thing. You should when I do a problem out, sometimes I keep these old ones. For Monday, I'm going to go through we'll probably finish up today. On Monday, anything we don't do for Chapter 17, I'll finish up, and then I'm going to go through every calculation that we will have. One at a time, we'll just go through them. So when I have a whole, these old problems I made up a couple of semesters ago. When I'm looking at it to verify everything, that's the first thing that I do. I see this, all right, and then I see, so it's Cn minus. I can figure out a lot of different ways, and so can you, but that's the first thing I look at. I know that's what I'm after. So here's the reaction that we want. And the reason, because all of these, when you see these problems, if you look at the exam guide, you look at those problems one after another, don't they start to kind of mix together? You know, you have to figure out which one, what is being asked here. Well, one of the things is, for this one, this is the only problem where I ask for the equivalence point. So what we're finding, well, after we do a little bit of work here, all we're doing is a salt solution problem. We already did this. If we knew what the concentration was of the salt solution, that's a problem we already did. Here you're figuring it out. You're figuring out what the concentration will be. Okay, so we'll do it over here. So we have HCN. We multiply these together. That's going to tell us the moles of HCN. Then we're going to divide by this concentration. That's going to tell us how many liters of the solution we used. That'll give us a new volume. We know our moles. We divide by our new volume. We have our new concentration, and we're ready to go. All right, so let me get rid of this here. And I'm going to actually move that because it's getting in the way of the calculation. All right, so this is just to let us know what happens. That's not the equation we're going to use, so I'll get rid of that. Okay, so what you do, you're mixing things. If you're mixing things, you're going to have to do this, the volume times the concentration to find moles, figure out the new volume, divide by it. Okay, so we'll always have to do that. Titration always works the same way. This. So this is going to give us the moles of HCN. We know it's 1-to-1. So 0.2 times 0.8. So this is 0.0160 moles of HCN. Now you can go directly and just say this is equal to the moles of NaOH. But I'll just show you how we get there. It's 1-to-1. So I'll go through all the math. We won't skip anything. According to that equation I had up, for every mole of HCN that reacts, 1 mole of sodium hydroxide reacts. So it's 1-to-1, so we end up with the same number. And I'm just going to write it as OH minus, because that's what reacts. You can carry the sodium through if you want. It just gets to be a little difficult dealing with that. So 0.0160 moles of OH minus. And we're using this equation from Chapter 4. I want to find the volume of OH minus that we use. So the volume is equal to the moles divided by the concentration. So we went through this to figure out the moles of the acid. And we don't know anything further about, we don't know how much of the sodium hydroxide we added. So we need to figure out that much. If this was 0.8, then we know what it is. It's 20 mils. But it's not, so we have to do a little bit of work here. So we figure out the moles of HCN, which must be equal to the moles of the OH minus. You divide the moles by the concentration of the OH minus. And I'll write it as this. So 0.016 divided by 0.5. And this comes up to be 0.032 liters. That's how much we had the burette. That's how much we added. We added 32 mils or 0.032 liters. Okay. Then we know that 0.016 moles of HCN, for every mole of HCN that reacted, we produce 1 mole of CN minus. And let me write these equations over here. I had them on the board, but just so you can see where these numbers are coming from. I want to keep pointing to it, but it's hardly only the one screen, one board there. So we have that. Okay. So took the moles of HCN, and according to that, for every mole of this, there's 1 mole of sodium hydroxide, which is just OH minus we're interested in, so we know how many moles of OH minus we had. So this gave us the volume of the OH minus that we added, so that's going to give us the new volume. But we also see that for every mole of this that we used up, we created a mole of that. It's the CN minus that's important. Again, you can carry the sodium ion through, but eventually you're going to get rid of it because it's going to get in the way. Okay, and once I get the numbers here, I'll show you a little bit of a shortcut. So the concentration of the cyanide is equal to 0.0160 moles, and divided by the new volume, which is what? We're going to take that 32 mils and add what to it? Was that? No, that's the concentration. Yeah, because that was what was in the beaker. So we had 20 mils, and then we added 32 mils to it. So this is going to be, and we have to be in liters. So the 20 mils, whoops, and then the 32. So a lot of work to do, and I'll go back through it too. And then on Monday I'll go through one of these. Okay, I just want to make sure they had get the most out of this, because these are advanced problems. There's no doubt about it. A lot of things going on. So this is going to be 0.308 molar. Okay. So now we have the CN minus, and we're just going to put it into this expression. If I had just given you this number and I said, here's the concentration of CN minus, find the pH. This is a salt problem, so we've already done it, so you should be able to just plug it in and you're set to go. But we had to find this number this time, so it took a little bit more effort. Okay, and we still have one extra step to do before we finish this up. Okay, so I took what was in the beaker. We knew there's 20 mils at 0.8 molar, figured out the moles of it. Now notice, this is 0.016, and according to the equation, it's going to be the same number of moles of OH minus, and it's going to be the same number of moles of the salt. So finding this allows you to find the base that you'll need for this calculation, and lets you find the salt, so you can finish this one. So it's all the same number, because it's 1 to 1 to 1. Okay, so now we have our concentration. Now we can start to go to town here. This is back to, notice that we did all of this work, and what do we come back to? Minus x plus x plus x. So it's the same problem. All it was is that you have a lot of little calculations to do. Just got to keep track of them. That's the big problem. And then you're ready to go. Okay, so is this a Ka problem or a Kb problem?
Okay.
It's got to be Kb. Did I give you Kb? No, I gave you Ka. So you have to change it. So if you see this, if you're given this, and you recognize what you're dealing with, this is a conjugate base, it must give OH minus, so this has to be the expression, but this is a Ka problem. I gave you Kb, or Ka, so we need Kb for Cn minus, which is going to be equal to Kw divided by Ka, and I have to give you the Ka, and it's a little crowded there, but and this comes up to be 2.04 times 10 to the minus 5. And that's our Kb. So one last thing. Now we have it all. Now we're back to just a very straightforward problem. The approximation definitely holds. This divided by this is greater than 100. Whoops. And then we solve it, 2.04. So this is really a problem that's combining almost everything that we learned in Chapter 6. And that's why it's taking so long, because it's doing everything. We're doing everything in this problem. We have acids and bases, Ka and Kb. We have a salt solution. This is it's like technically the end of a buffer problem if we went too far. So it has everything in here. And then this is the concentration of OH minus. So if we take the negative log of it, we get POH. But I wanted pH, which is generally what I want, just to verify that for each problem. There's a couple where I'll want POH. Could even be other things that I want the concentrations of other components, but pH is going to be the main one. And so this comes up to be 2.6. So pH is going to be 11.4. Okay. So that's the type of problem. It's going to be a weak base, strong acid. It could be any weak base. This could be KOH or LiOH. I won't put calcium hydroxide because that's 2 to 1 there. So, but you have to figure out the Kb for it. You have to figure out the moles of the acid, moles of the base, the new volume, the moles of the Cn minus, which is going to be the same as these. So this will be the conjugate base divided by the new volume, and then we can finally do a salt problem. So from here down is just a salt problem we did before. All of this is what you have to do during the titration. So it's the first time you've seen it, and it could be a little dizzying, but it's all there. The procedure's there. So I'm not going to do another one. I can do one after class definitely, and then on Monday I'm going to run through it. But at least get this down. Okay. And that, I would say, aside from the buffer, is probably the toughest problem that you'll find in 16. Okay. Let's see what else we got here. Okay, any questions on that? Fun stuff? Fun meter? 7.5? Yeah, I think 7.5. And that's 16. That's all that we're doing there. But you should see that there's could certainly have given you a weak base and a strong acid, but it would have been you would have the Kb for the weak base, so you need the Ka for its conjugate acid. It all works. The math is all the same, but that's what it's going to be. It's going to be a weak acid and a strong base, just to keep things as clear as possible. All right. That was chapter 16. That's why there's only 2 chapters on this exam. Chapter 17 has some problems, some tougher ones, but not very many actually. And it is theoretically possible we'll finish today. I'm not going to rush it. So if we need about half an hour on Monday, we'll do that. But let's just go through. But the math is going to be the same. We actually simplify things to some degree for what's called the solubility product. Okay. So chapter 17. But if you look at the exam guide, you can see that chapter 17 just takes up about 2 pages, or less than 2 pages, compared to the chapter 16 stuff. So this is solubility products. That's what they're mainly. We're going to do a little bit of what's called formation constants as well. Okay, so what we, in 1170, in any course, any of the basic courses, you could argue in any course, you're always lying to the students. We lie out of love. You don't want to see it all. You might not have the math background yet to see it all. You don't want to see it from the ab initio point of view for quantum mechanics. You don't want to know every nitty-gritty thing. So we make up stuff that's pretty close to the truth. One of the things that we say is that there are insoluble salts. That's not true. Everything dissolves to some degree. If you take a block of gold and stuck it in water just for a moment, took it out, there would be some gold atoms left behind. Not many, probably nothing that you could actually detect, but everything dissolves. So we have this, we say silver chloride. We say that's an insoluble salt. All you say is it's a slightly soluble salt. Everything's slightly soluble, but sometimes it's so slightly soluble that the ions would be very difficult to detect. So we say it's insoluble. So that's the lie there. It's like we're just kind of exaggerating the truth. When we say that things don't dissolve, we say not very much, so little that you probably don't want to, you won't be able to figure out how much is in there anyway. But sometimes it becomes important. And this coupled with other reactions can become important. And one of the big things is a lot of things we want to leave in solution. We want them over here. And if they're not very soluble, if we put too much of a concentration here, Le Chatelier's principle says it goes back this way, and we get a precipitate. And you really don't want that to happen on an industrial level. We have a chemical system this size of this room, and it accidentally precipitates everything out. You don't just put in a little water and stir it real fast anymore. Now you're talking about lawsuits and going to prison for negligence, maybe, and some environmental disaster. So the keeping things in solution is often the best thing, but sometimes you want to precipitate stuff out, and this allows you to do it as well. Okay, so we have this stuff here. Now, this in general doesn't dissolve enough to see, but we're going to determine how much actually goes into solution. But this is the equation for this salt. And if you write the Kc for it, you can see that it is the concentration of silver and chloride, and what goes on the bottom. Yeah, it's a solid, so nothing. So for these problems, we never have to worry about the left side. We don't write anything down here. We don't put it in the Kc equation. So actually, in some ways, it's simpler. The big problem, and because of its importance, we call this the KSP, the solubility product constant. So you should know the names of these different K values. And that's right on the exam, Ka, Kb, Ksp, Kf, Kd. We're going to have all of those. And I think I just have you write them. I don't think it's even multiple choice. So don't get it wrong. If it's multiple choice, what I do is I'll say something like Ksp. If for a wrong one, Ksp is the sign product, or I'll say the science project. The science paradigm. The science paradigm constant. And people say, yeah, that sounds scientific in circles. So make sure you know them well enough. But you probably will have to fill in the blank. So this is what we're after before we do a calculation here. Here's where it gets a little tricky. This is pretty easy now. This is just 1 and 1. But if we have something like, what do we have? Can't think of one offhand that's going to be, oh yeah. So magnesium arsenate. Now you should know the charges on this, but if you don't, as long as you get the ratios right, I guess it won't matter, but you want to know that magnesium is +3 and arsenate ion is -3. But if you forget, and you have this as +3 and this is -1, it really doesn't matter. It's these numbers that we're interested in. So if you write out the KSP expression for this, it's going to be magnesium cubed, arsenate ion, concentration squared. I don't know why I'm writing like that, because we don't need anything on the bottom. But now you see that it can get a little wild. Now we're talking about cubes and squares, and when you're multiplying all this stuff together, and there's unknowns in there. If you have x's in here, then it can get up to x to the 5th. So it can get pretty out of control. Okay, so let me write out all the possible ones. It seems like there's all these different ones, but really it's 1 to 1. This is 3 to 2. Let's do out. I can't think of one. Let's do. And then I can show you each of these in turn. So if we do, this is going to be KSP. Now that's 1 to 2 for the ratio. So 1 to 1, 1 to 2. So actually, for you to try, I'm just going to put up these ones on the board, and you try to come up with the full form of it and the KSP, because that's one of the things that you have to do. So I'll say, what's the KSP? The form of the KSP equation for Hg2O. So try that, and each of these will have a different kind of ending when we're dealing with unknowns, when we're dealing with x. So it's good to see them all. So what's another one here? Okay, got 1 to 1, 1 to 2, 2 to 1. And then we have see what we can do with that, and then oh yeah. You should be able to figure out how to break them up into their ions. With when there's parentheses, that's fairly easy. Here's one that often gets students because they forget their chapter 2 stuff, surprisingly. 7 months or so. So try that one. And let's see, so we got 1 to 1, 2. And then, yeah, that's good. That covers pretty much everything. All right, so when you see this, what you would do is you just see you're breaking it up into its cations and anions. These are always insoluble salts. So they mostly lie to the left, but there's always a little bit that dissolves. And for this one, you write solid. And then for this one, again, not knowing the charges, if you thought this was +2, then you think this is -6. But when we do this out, you see it's really the coefficients that we want. And then for this one, what does this break up into? So I'm figuring out, because this is probably the only one that's really going to do make you miss here. This is mercury 1. Mercury 1 ion is a diatomic ion. It stays intact like that. So this would become this. But since it's in the, I don't know if it's the chloride that's in here, but I know the mercury one is in here. Yeah, it is the chloride one. Like that. Okay. And I'm just going to get rid of this. Let's find we have 20 erasers here. Let's use them. Okay. And we'll go down the line here. We got the KSP, and then this becomes KSP A plus, Ag plus squared. Always solid on the left, so we save ourselves a little trouble there, but it's those coefficients, because everything in chapter 6 was pretty much 1 to 1, but now we got different ratios, so we got to keep track of those. And then the KSP for this is silver cubed. Okay. So, and that's it. It can be 1 to 1, 1 to 2, 2 to 1, 3 to 1, 1 to 3, 3 to 2, and 2 to 3, though I don't have 2 to 3 up there. But yeah, we'll do that at the end here if we need it. Okay, so this one would be, I'm just going to finish this one up, but then erase it just so I can have some room here. That. Okay, so you should be able to write out, if I give you a salt, you should be able to write out this whole equation and then write KSP. And we're going to do so many of these calculations, hopefully that is not going to be a big deal. This should be a problem you look at and say, oh great, do it in 30 seconds and get it right. But make sure it's multiplied. You're using the coefficients here. They've all been 1 to 1, so that's why I keep pointing it out, because you get so used to just the acid-base stuff to just use 1s. Okay, so now I'm going we're going to lower this. Now we're not going to do the calculation out, but let's say, so if we want to do this problem, we'll do this. This is solid, so this is certainly losing some of the mass, but its density is staying the same. It's just lumped up on the bottom. So we don't do anything over here. So this becomes plus x, x for the ice table. That's what it's going to look like. So if we put those values in here, then KSP is equal to x squared. So when you do this one out, all we have to do is take the square root of KSP to find x. Okay, for this one, I'm just going to lower this again so we can put the ice table. So you can just see, and with each of these, this pretty much covers all the possibilities. You could envision an ion that had like a 4 and a 7 here, but they just, they're not common. That's about it. So if we do this ice table out, what goes here? Plus what? Yeah, plus 3x. Don't forget that 3, because that'll make a huge difference. Or potentially it could make a huge difference for your answer. So you put these in. This is 3x cubed, 2x squared. So that's going to be 27x cubed times 4x squared. So this is going to be 108x to the 5th. So if you have to solve for x for this problem, you're going to have to take KSP, divide it by 108, and then take the 5th root. So we'll talk about those. Okay, how about over here? And the reason I'm going through these is because if I do this, I've gone through all the possibilities that of these ones. And just so that if you see at the end of the problem, x squared, be happy, that's one of them. If you see 108x to the 5th, that's a possibility. But you can see it can't be anything else. It's not going to be it's not going to be 99x to the 5th. It has to be 108 x to the 5th. If x to the 5th comes out, it's going to be 108. For this one, we put x, 2x squared. So this is going to be 4x cubed. This is a very common one that we do. So if you're solving for x, and some of these problems we do, you'll end up with 4x cubed. How about here? This becomes 2x squared, x. So this becomes 4x cubed again. So whether it's 1 to 2 or 2 to 1, doesn't make any difference because it's a product. So if this had been 2 and 3, we'd get the same thing. So that 4x cubed is one of them. So we have x squared, 4x cubed. So just go up to this one. This should be to the 4th. Put this in. We have x. So this comes up to be 27x to the 4th. So if it's x squared, it's just 1. If it's to the x to the x cubed, then it's going to be a 4 in front of it. Is x to the 4th, it's going to have a 27 in front of it. You can see that here. Whichever side this is on for the coefficient, 3 to 1 or 1 to 3, it's going to be plus x, plus 3x, plus x, x. It's going to be 3x. So for these problems, the worst you're going to have to do is take the 5th root. It's either going to be square root, it's going to be the cubic root, it's going to be the 4th root, or it's going to be the 5th root. That's it. So putting them together, the x squared, 4x cubed, 27x to the 4th, or 108x to the 5th. It's not that we couldn't have coefficients that are larger, we're just not going to see them in that table, and they're not going to appear on the exam. I'm not going to go out of my way to give you some crazy numbers like 11 and 17, but you can see what you would do. But these are the ones that you'd be looking for. So if you find that you're doing the problem out and you see 4x cubed, that's great. If you find that you have 17x cubed, better check. I don't know if there's any way to get to that. Okay, so that's what we're after. You can see that the coefficients make it a little tougher, but really losing the left side here makes it a little bit easier. So this is the kind of thing that we're going to be doing. So we'll go through all the different calculations here. I'll start with this one. I won't do them for all of these, but let's just get rid of this guy here. So that's just to let you know. I noticed that when I was a student at first, you just think, man, it could be anything. After a while, these same unknowns kept coming up over and over, and say, yeah, this coefficients can be from 1 to 3, some combination of them, and this is it. These are the only possibilities. Okay, so if we have this, let me start from the beginning here. I'll get rid of this. And I say, what is the solubility in grams per liter? I will always tell you what the units are, but if you see solubility, you think grams per liter. If you want to say moles per liter, you'd say molar solubility. So what is the solubility of AgCl? Okay, and then I have to give you KSP. So KSP for AgCl, that will be right in the problem if this were the one. 1.8. So what we want to see is how much of the silver chloride. So I say we were lying to in 1170. This does dissolve a little bit. Let's see how much. How much goes in grams for a whole liter? Let's see if it's something that we needed to worry about. Okay, so you get your ice table. 0, 0, plus x, x. We don't know how much of this went into solution. We know some did. But whatever went in for this, the same amount went in for here. So we know that's safe to do this. If this is x, this must be x. We then put in our KSP expression, because we know we have our KSP value, so that's good. X squared is equal to 1.8 times 10 to the minus 10. So x is just going to be the square root that. So this one is particularly easy. That's as easy as it gets. So this is 1.34 times 10 to the minus 5. And this is moles per liter. So this is the molar solubility. So just watch on the exam. I might ask just for the molar solubility because that's x. And I should point that out. X is always molar solubility. So if I ask you to find the molar solubility for anything, you're finding x. Even if it's crazy stuff here. So, well, what about this one? Well, this stuff here, I got to find the molar solubility. Find x, you got it. Divide by 27, take the fourth root, you find x, you have the molar solubility done and done. That's it. So it's really a very good thing to know, because you can find it out. But if you're thinking that it's this whole convoluted thing, and then you get to the end and you go, oh, it's x. So x is always molar solubility. Okay, but we don't want molar solubility. We want solubility in grams per liter. And so that's 107. Actually, I think 108 plus 35.45. So this is 143 AMU. On the exam, you might have to find the value yourself. I'll give you the periodic table. But if I just want to give you that right off the bat, then I make it AMU, which means grams per liter. So this is easy to type in. That's why I do it. And they mean the same thing. So you have that. So you take 1.34 times 10 to the minus 5 moles per liter. 1 mole is 143 grams. And this comes up to be 1.92 times 10 to the minus 3 grams per liter. So is it something we have to worry about? Not normally, because this is about 1,000th of a gram, 2,000ths of a gram. So this would just barely, if you had this much silver chloride, it would just barely register on our balances. You'd have to close it off because the air currents would bobble it around. You wouldn't be able to tell. So that tiny, if you were to take it out, it'd be this tiny little, it's white, it's a white substance. So you'd see this little tiny white dot, put that into a liter, and that just barely dissolves. So there is not much of this that goes into a whole liter of water. That's why we say that it's insoluble, because in most cases, that's all we have to worry about. But if this silver were to get a hold of something else, if it goes against something that's more insoluble in the water, it can precipitate it out, even that small amount. Okay, let's do one here that's a little trickier. All right, try this, and then we'll make sure we work on the roots. We know how to find the third, fourth, and fifth roots. Okay, so what is the solubility in grams per liter of magnesium phosphite? And we'll say the KSP is 1.34 times 10 to the minus 15. And I'll determine the mass here. So it's 31 plus, what is it? 48 times 2. And then 24.3 times 3 plus recall. So this guy is 231 AMU, we'll say. Might be in the problem. If not, you have to, most likely I have you look up this value in the periodic table. Just make sure you can do it. But for some of them, after a while, I'll say, yeah, I think they got it. They got the feel of this. I'll give them the values. And then I'll also ask what is the molar solubility. Probably wouldn't ask them for both of them, but here I want to just so you can see. And it's always going to be X for molar solubility, which is molarity, by the way. That's all it means, is the molarity. But since it has a special case here, because we're talking about insoluble salts, we say molar solubility, but it's really just the molarity, moles per liter. Okay? All right, so you get magnesium phosphite. Got this here. That's a solid. Breaks up into 3 magnesium plus 2 phosphite. That's your expression, so you got to get used to this kind of. I'm sure you're used to the acids and bases. This one, in some ways, is easier, but there's a lot of stuff. Those coefficients can get large. So we have, this is 0, 0, plus x, plus 3x, I should say, plus 2x. Wanted to see that plus x. We could do that here, but here we have to be careful. Then you put it into the KSP expression. This is going to be 3x cubed, 2x squared. And that's going to be equal to 1.34 times 10 to the minus 15. And those values, it can get pretty small. What do they have here? 10 to the minus 50th they have here for silver sulfide. Ebbing used to have one in the back of the book. You might still have it in the back that is 10 to the minus 103. So these can get astoundingly small numbers. So this is going to come out. Make sure. Oops. So we got this, and there's on one of the videos for this, I put for one of them I put 105 x to the 5th, and there's a note that says it's changed, but a lot of students miss it. Was it 105 or 108? It's 108, but as I was doing them out, just sitting in a room alone, doing these things out, kind of lose track of things, and I guess I just doubled up in the 5s there. But it didn't make a lot of difference, but you want to make sure this is 108. Okay, so we have this. So we divide by 108, and we have x to the 5th. And this is 1.24 times 10 to the minus 17. And then we have to take the 5th root. Now, if you take the square root, that's x to the 1/2. So and we have a square root button, so that's no problem. But if you just put in x to the 0.5, you're fine. The cubic root, that's going to be x to the 1/3. So that's x to the point. Now it has the root button on here, but each time I change calculators, it's always hard to find, and we only do it for here. So what I would do is I just take, let's say, 5. I just raise it to the 0.3333 power, and it gives me everything that I need here. So I never bothered to learn it. You're free to do that. I didn't bring my calculators, but if you wanted to borrow one over the weekend, you certainly can to get used to it. But this one, x to the 4th, so this is going to be, that's x raised to what number? 0.25. It's probably the easiest way to go. It's very fast, but you are free to learn to use the root function, but we only do these, a few of these, and then, so what I would do, for me, what's the easiest to do without having to keep figuring out that different function from year to year with the different calculators, I just do it to the 1/5 of the 0.2. So it's 1.24, so minus 17 raised to the 0.2. And this comes up to be 4.16 times 10 to the minus 4 molar. And that's x. And what is that? What else is that? That's equal to x, so molar solubility, yep. So this is our x. So this is our molar solubility. And yeah, and at the break, I'll head back to my office. If you do want a calculator, if you want to borrow one of these and just get used to it over the weekend, that's fine by me. But just let me know so I can bring them back. All right, and then what we got here? So we got a couple of things we got to do here. 10 to the minus 4. Oops. And that's moles per liter. And then for every mole, that is going to be 231 grams. So the molar solubility, times 231, and this is going to be 0.0961. And you can expect it to be a number. Usually it's going to be less than 1, and a lot of times a much less than. Though these are very different from each other as far as the answers, you can see we just do the KS, we put in our x's accordingly, put them into the KSP expressions. This one turned out to be very simple, just take the square root. Here we have to take the 5th root, and it takes a little bit more time, and then you multiply by the formula weight. Okay, did that. Okay, number 25 is to find the KSP. So we do it backwards. Instead of giving the KSP, we find it. I don't have that one on the exam. So you can just cross that one out. We'll do that for one of the labs. We actually do that calculation. We can learn it there. 26 is what we just, number 25. It says a 2.5 liter sample of solution of lead bromide is evaporated to dryness. It's just kind of the reverse of this one. It's not that it's not important. We're definitely going to do it for the lab, so you're going to learn that calculation, but yeah, we won't worry about that one. Okay, so because I just finished up the exams, and I mean I could put every single one on there, but I cut away 5 of the calculations, or I combined a couple, so we'll talk about that on Monday. But yeah, so that's reasonable. So you can see it's the same kind of stuff, just that we have nothing over here. That simplifies it. The coefficients make it a little trickier. You have to deal with these roots of numbers, so you got to get that under control. But really, it's the same kind of math that we've done. All right, let's take a 10-minute break here. And if you do want a calculator, let me know. That you can use over the weekend. That's fine by me. So we stand. Yeah.
Is it my helpful?
Mm-hmm. Yeah. Okay, anybody else? I'm going to head over to my office. So that's 2, 3, 4, 5, 6. Anyone else? Absolutely no problem. Once we get up to about 20, I'll have to bring my briefcase, but so 6, all right. So, yeah, I can carry those in my pocket. I think this coach should be able to handle it. Okay. Yeah, so we're doing pretty good. I think we'll have a couple of things to finish up on Monday, but then I'll go right through this. Now, you guys are going really fast in the lab, which is fine, because the numbers seem fine. So normally, for that last lab, we'd have at least 2 or 3 people that would have to go back today. But since we don't have that, we have that free time. I figure what we'll do is finish up this, and then I'm going to do the calculations for the lab. And then after that, it's going to be a much more relaxed thing where I can put some problems on the board. You can try to solve them. I think the buffer one would be a good one to try. And you just go tonight. You can work on your own. You can work in a group. and then just show me the answer. Put it on the board. If you want to work on the board, you can. And we'll just make sure that the big problems are ones that, and any problem you want to do, I'll just make up one and you can try it. So if you're doubtful of something, we just did this, but for the acid problems, if you want to see one, like a common ion problem, I'll put one on the board. Try to do it. I'll check it, and we can do that. So that'll be up to you. But we have that time, so I want to use it if you need that. But I don't want to be lecturing for 3 hours. I certainly could get everything done by 4 if you wanted to keep going. But yeah, there's a point where their brain kind of breaks down, including me. So, but yeah, so think about that. If you want me to work through some problems or let you work through them, I will definitely put a buffer problem up here. And I was thinking like a triprotic acid problem, because those are the big ones. The fractional precipitation one is as well, but we haven't got to that one yet. So if you can, each of those, the triprotic acid and the buffer are each worth 10 points. So those two together are 10% of the exam grade. So you want to know how to do those. And any Wednesday where no one has to go back to the lab, I have no problem doing that. You can go through anything that you want. I don't want to do your homework for you, but if you want to bring your homework in and I can help you, I can give you hints on going along. But I think I might have said that when we were doing homework and I was helping students out because it was the first time we had it. So I was kind of interested to do them. And I was doing out this homework problem for one of the students. I look up and he's on his phone. It's hilarious. It's like, got that done yet, Champagne? I said, I'm working as fast as I can. And I was like, no, get off of you. So I thought, okay, now I'm not doing the homework for people anymore, but I will definitely give you hints. And if it's really tough, I will. But yeah, if you want to do your homework with me, that's fine too. Ask any questions you want. That guy was a piece of work. I'm sure he's doing fine. He wanted to be an engineer. All right, 6. Let's get that. 6. And then, when we hit them, there's a couple other problems that we won't be doing either, because they're kind of copies of the ones that I think are more important. But once later on the chapter here. So 6. And then, who has their lab numbers? I just want to see. I'm thinking. Yeah, that's what I was saying as well. So, yeah, after the lecture, I'll go through that too. Oh, and what did I say for KHP? It was like 0.2?
Yeah, 0.2.
See that on 11.2. Got it. Thank you. All right.
There's breaks, because of the actual magnets in it, it's hard to. It's a little for some. Yeah, this took me 5 seconds to find it, I did 2 seconds to find this, and doing it. The magnet.
Yeah. What?
I got paid 2.5 cents to make it. It's worth every goddamn time.
Oh yeah, I have something like.
Magnets don't fuck with me, what are they?
No, I have that
What are they?
parking lot.
Is it Adderall? I'm looking for Adderall.
And then I have trying to over this side. Just like that.
Is our test next week?
What?
And they have that little bar thing.
It's only 2 chapters.
And then once you like go through in and out, but I'm not gonna break that.
Hey, you're out of shifts for that one.
You know there was old pictures in your house? Did you read about that? Like these two people, they brought in like a and a Bible. What did you read about that? And it had the cities that have like shootings in it.
Yeah. Someone's getting an idea of
So when you like stake after how many you should build it,
Bess, you put the thing back together, they're gonna go. That's it? That's done? Drive and see how it is, shotgun, brakes. It, pads it in the computer probably? Pads?
No, do it on that. We got one. One side with it. Matt's got one, I got one. We just had the semi-broken one. Last George showed. That's the most. It's on Ambrose. Yep, that's more of a Sunday night, Monday morning.
All right. Who wanted a calculator? There you go. And make sure it works. I checked them all before we came over. Yep. Yeah. Anyone else? It's good. They brought a bunch. All right. Well, yeah, just remember to keep them for the exam, but just turn them in before the end of the semester. And after this exam, we really don't have much in the way of math. We now shift almost into pure theory, just a few calculations. So if you like the math, then you'll be sad. If you don't care for the math so much, we're over that. We're beyond that until the final. We just start doing mostly theoretical things. So there's sometimes there's a shift in the grades. The people who really love the math, their grades are high, and then they drop off, and they blame me for that. I say, well, I told you. And then the people who are doing poorly, but the theory, they like that stuff, and it goes up. And then we do a lot of different chemistry, usually 1 or 2 chapters people find interesting. That helps. I think the nuclear stuff is usually a big hit. Okay, but we got to get through this. Now, all right, so that's the basic idea there. All right, so we'll see how many. Yeah, I'll probably save the KF, KD stuff for next time. All right, so now we got to do a common ion problem. So there's only stuff on the right this time, but we'll start with something here. So it'll be something plus a number, for instance. You should know how to deal with that. Oh. Okay. Yeah, so we have. All right. What is? Oh, this one's bad. Is. All right. So everyone understands the molar solubility versus solubility. So solubility, you're just multiplying by the formula weight. So for the rest of these, I'm just going to make it molar solubility to kind of speed things along. But so what is the molar solubility of, I need a compound here, something different. Oh, here we go. All right, so instead of trying to dissolve this in water, we're trying to dissolve it in a solution that contains spectator ions that we don't have to worry about, but then chromate. So chromate is going to be the common ion. And I have to say that KSP for silver chromate is 1.10 times 10 to the minus 12. Okay. So you're given KSP, so odds are you have to write this expression. Might as well write it out, see what's what. So, all right, now this sodium, the sodium's going nowhere, but you can see that this is 2 to 1. So the concentration of the sodium should be 2 times this, but we don't care. And then it's going to be 1 times this. So what this is going to produce is 0.4 molar chromate ion. That's going to go in there. That chromate didn't come from here. This is producing chromate ion, but the salt is producing nothing but it. It's a soluble salt, so all of it goes in. So when we start the problem, there's 0 silver, and then there is 0.4 molar of this. So you'll be given a salt. It's a soluble salt. It'll be sodium or lithium or potassium or something that we know is definitely soluble. I usually go with sodium because there's no doubt about that one. That's the one we use a lot. And then this is going to be plus 2x, and then plus x, 2x, and then 0.4 plus x. Put it into the KSP expression. 2x squared, 0.4 plus x is equal to 1.10 times 10 to the minus 12. So same idea. Can we try to use the approximation on this? Yeah, sure. I mean, it's math. What we were dealing with before was just telling us that if we have this expression and this number divided by this is greater than 100, then we can ignore this x and know that we'll have less than 5% error. That's all. The math is there. That's all it's saying. How we got this equation is inconsequential to that error. And the larger the number, when we divide this by this, we end up with something on the order of close to 1 trillion. So yeah, the error here is going to be very, very slight. So we can ignore that. And now we see that it's not going to be too bad at all. But with these coefficients, that means we got a few more things to do. So we've got to be careful about remembering all of our numbers that we need to use. Like so. And then divide by 1.6. And I'm just doing out every step, just make sure you see where it's going, because as opposed to the acid-base stuff, the number in front of the x squared was always 1. So now we got a little bit more to worry about. So x squared is going to be equal to 1.1 times 10 to the minus 12 divided by 1.6. So this is 6.88 times 10 to the minus 13. So x looks like it's going to be 8.3 times 10 to the minus 7 molar. So is that the molar solubility? Is it x? And that's molar solubility, yep. Always and always. So it doesn't matter that we've added some other stuff here. Doesn't matter that there's a 2 here, that we're squaring here. We're after the x. And the reason is because we're trying to find the molar solubility of this. There's always a 1 in front of this. So when this breaks up, say one of these breaks up into 2 and into one of these. But how much, if it breaks up by 2x here, then it must have broken up by x here, or we lost that much. So it's always going to be x that this comes from. If it helps, you could do it this way. You'd say that a small amount of it goes into aqueous and then breaks up like that. And so you could say, since this is aqueous, so a small amount goes in intact. So this would be minus x, or this would be x, so you lose all of the x, and then plus x plus 2x. But that's a little bit of extra work to show, and that's not what it does anyway. You don't have this formula unit go into water and then break up into ions. The ions just break off of the solid. But that's what's really happening. So you'd say this is x, 0, so this would be minus x, plus 2x, x, 0, 2x, x. But we'd have to take into account that aqueous, so it gets a little bit out of hand, but that's where the x comes from. That x is always 1x for that compound. So if we know this, then we know the molar solubility of this whole thing here. But we won't worry about that there. That's just an aside. Okay, so that's a common ion problem. and I could have certainly given you silver nitrate up there, and then the number would have gone here. So, a lot of things you can do. Okay. Now, let's see more or less what we've done. We dealt with the Ka expression, then we did a few things with it, and then we did the common ion. That's what we're doing here. And now for the special case of this solid here, we know if it shifts back this way, we call that precipitation. Le Chatelier's principle says that if we can boost up these concentrations, it will shift back. So we have that to deal with. So, what do they have here? All right, so that's the reaction quotient, if you remember that. So the QC tells us which way the reaction is moving. Now, under this, I think they call it the ion product, yeah. For KSP problems, but if I ask you for the name on the exam and you put down reaction quotient, I mark it right. But it's because of its special case here, because we're dealing with precipitation reactions, we call it the ion product. So if we have a reaction like silver chloride, and we want to see if it's going to precipitate, you would say that QC for it is going to be this. Remember the reaction quotient looks the same as the KSP, but it's not at equilibrium. We want to see, is it going to precipitate out? So we're right on the edge of something happening, so we're not at equilibrium, so we don't use KSP. So if QC is less than KSP, now just thinking of it as a reaction quotient, if QC is less than KSP, or QC is less than K, which direction should it go, left or right, if it's too small? Which direction should it go? Remember? Let me show here. If these numbers are too small, we want them to get, as the reaction goes, the KSP is where we're heading. If these are too small, we need them to get larger, it has to shift to the right. So this shifts right. If QC is greater than KSP, then we got too much of this. These numbers together are greater than KSP, so the only way to get to KSP is if we lose some of this, which means it shifts left. But in this case, we have a special thing that happens. It precipitates. PPT means precipitate. Also means PowerPoint, but originally meant precipitate. So if you see PPT, that means either that it's precipitating or it means the noun of it's the precipitate. And then this is also a special case. If QC is equal to KSP, you can say you're at equilibrium, but what's really happening in this case is the reaction is just ready to precipitate. Because if you're dealing with precipitation, you want to know when it's going to go. If QC is at KSP levels, all you have to do then, theoretically, is just add one more ion here, and it's going to start precipitating. So that boundary here, when QC is equal to KSP, that's a really good point to be at, because then right there, you can add a little bit more and cause it to react and precipitate, or you can just leave it alone. So these are the ones that we're after. So we're really, this is what we're looking for. Most of the time, we want things to precipitate, but in a controlled manner. Okay, so let's do a basic one. Yeah. All right, so if we already know the concentrations in the solution, we just plug them in here. And then we check it against KSP. Well, let's do one where it's a little more complex. Let's see. where you have to mix them. This is what we normally do in the labs. We take a solution, two solutions, and we mix them together, and maybe some cloudy stuff comes out. That's a precipitate. We want to know, will that happen? So mix 40 mils of 0.5. Get something that's, let's see, 0.35 molar barium nitrate with 60 mils of 0.00175 molar sodium chromate. Do you get a precipitate? And you can say that KSP for barium chromate is 1.20 times 10 to the minus 10. We're mixing things. So what do we do? So I made a point of giving you the concentration and the volume. We're mixing, so we're going to find the moles. Find the moles of this, divide by the new volume to get our new concentrations, and then they go into the K or the QC expression, which we're going to compare to KSP. All right, so you're given this problem, write out. Here you should know that these are spectator ions. These should form into barium chromate, but there's no doubt about it because I give you the KSP for barium chromate. So you should know that this is the expression you're after. So now what we have to do, remember when we did QC before, we didn't use the ice table because we're not going to equilibrium. We're just somewhere in the middle of the reaction. So when you mix them together, that's what possibly the start of the reaction. So what we need though is that we need to know these values. Well, we need to know their concentrations after mixing. So that's why you'll be given the volumes and the concentrations. So you're going to multiply those together appropriately, divide by the new volume. Now you'll know the concentrations, plug them in here, and then compare them to the KSP. So we do the same thing as we've done for these other ones where we mix. So what we do is 0.04 liters. I made those extra zeros because, and you can just do the sign. I just want to make sure that there's a chance that this will not precipitate. That's a really small number to get past. That. Take the volume and the concentration of the other ion that's important here. Going to leave off the sodium because we don't care what sodium does. It's not falling out of solution for anyone for any reason, so that's not part of the problem. Just that counter ion that will precipitate out with barium under the right circumstances if there's a high enough concentration. Okay, those are the moles. Those don't change. Mixing them together, we have those moles. That isn't affected by it, but the concentration is. So after mixing, the concentration of the barium is 1.40 times 10 to the minus 4 moles divided by what? What's our new volume?
100?
Yeah, 100 mils or 0.1 molar. We've mixed these, we've added these together. So 0.1. So that's just going to change it to 1.4 times 10 to the minus 3. And then the chromate is going to be 1.05 times 10 to the minus 4 moles over 0.1. So that's going to be 1.05 times 10 to the minus 3. All of that to get back to this expression. And we do 1.40 times 10 to the minus 3, 1.05 times 10 to the minus 3. And it's not going to be as close as I thought, but that's fine. And this comes up to be 1.47 times 10 to the minus 6. So we've mixed these together, and we want to know, does it precipitate out? So on the exam, I'll ask you to give me that number. Because then I'll also ask, does it precipitate? Now I don't just ask that one because you could say yes or no, you get a 50-50 chance, but I need to see this. QC is greater than KSP, and that means that we did have a precipitate. It definitely fell out. If it had come up to be 1.47 times 10 to the minus 16, that's too low, so no precipitation. So for some reactions, you want it to precipitate. Others, you don't want them to. So in this case, if you wanted to leave everything in your reaction vessel, then you got a problem. What you'd have to do is you'd have to dilute it that much more before you mix them. Because once something has fallen out, it really takes a long time to get it back into solution. It's not as easy as just putting more water in there. That will do it, but it will take a long time to come to equilibrium. All right, so this is a problem where we have to do the mixing, do this stuff here, find the new concentrations, and then we can do the job. So that's it. We are doing just like we did for the titrations and for the buffer. Okay. So we did that one. All right. Now for the last. The fractional precipitation problem. Sometimes you have mixtures of solutions and you look at their KSPs and they're such that they allow you to precipitate out one thing and leave the other two ions behind. So the first one starts to precipitate out and then the other two are left behind and you keep increasing the concentration, then the second one comes out and then the third one. So, and you can do as many ions as you want. So I'm going to use the one from the exam guide just because I got to get these numbers right. If you make a mistake on the numbers, it can get pretty bad. So I'm going to assume I knew what I was doing on that. I do have the answer key there. So unfortunately, I have to do that. But for Monday, I'll do another one, and I have a whole new set there. Let's do this out. All right, this one takes a lot of work. This is one that's worth 10 points on the exam. It's you have a full blank page to work with. But it's extremely procedural, and when students get it, it's remarkable to see. Some people have so much better handwriting than I do. And when they put it down, it's like the answer key. It's even better than mine. I got my answer key, and I said, I'm using this. And it's so beautiful, just boom, boom, organized right down the line. And they'll have stuff on there, and say, oh, I forgot to put that in there. Oh, yeah. Now it's up here, I got some scribbled up mess up in the corner. But there's like, and I know that they didn't copy it from anyone, because I just made up the numbers. They can't have taken it from anywhere else. They did this. So this can be done really, really well, but it is a gigantic problem. So we got to do this out. So fractional precipitation. So I'm going to run through this, and then undoubtedly we'll have time on Monday. Even if we don't have as much time as I want, we'll do this one before we go to lab. But I'll do out the larger problems. But yeah, so it's about 4.5, 5 hours from here. I'm just going to write around the board down the hall. No, this. I mean, if I didn't speak, if I just wrote this out, it'd probably take about 5 minutes. So, but it might take a little bit longer than we normally do. But we'll be done before 3. So let's just focus on this. So what we have, use these numbers. So a solution contains 0.14 molar magnesium nitrate. That nitrate is insignificant here. It has no consequence for us. It's just there to allow us to bring this in. So it's the magnesium that we want. And the nitrates is what, it'll be metal ions that are in solution. So we have 0.14 molar calcium nitrate. So it's the calcium we're interested in. And then 0.14. But you do it for completeness. So if somebody actually wanted to perform this reaction, they'd need to know. If you said magnesium, they say, well, magnesium acetate, magnesium nitrate, well, what do we use? So that's what, but we're interested in these 3 metal ions. Okay, so that's what we're after. Notice they're all the same concentration. They don't have to be, but if I do that, it makes it a lot easier on you to solve the problem. So I normally do that. And then I have KSP for magnesium selenide is 8.31 times 10 to the minus 4. KSP for calcium is 1.5 times 10 to the minus 11. and then the KSP for barium selenide is 2.55 times 10 to the minus 7. Now here's what I ask. I ask for what is the concentration of the selenide ion needed to precipitate each metal ion, to begin to precipitate it? What is the order of precipitation of the metal ions? When the second ion starts to fall out. So we're precipitating them out in turn. One falls out, and then we keep upping the concentration, and then the second one falls out. Then we keep upping the concentration of the selenide, and the third one falls out. So first I want to know what order do those fall out at. Then I said when the second ion begins to fall out, how much of the first ion is left? Because we started precipitating out the first ion, but it doesn't mean it's all out of solution. Actually, there's no way to get it all out. And then the final thing is when the third ion starts to fall out, how much of the second and the first are left in solution? By 1%. So a lot of stuff here. Now we're going to figure this out. Which one of these falls out first? Magnesium, calcium, or barium? Well, I will say that it is the calcium falls out first, then the barium, the magnesium, done and done. Easy as can be. The only reason this works is that they're the same concentrations, and this is 1 to 1, 1 to 1, and 1 to 1. If that's the case, and it will be on the exam, you can tell the order just by looking at the KSP. The smallest one falls out first. The second smallest, falls out second, and then the largest one falls out third. We're about to prove that. You're going to prove it mathematically, but this is true. But if this were Mg2, and this were Ca3, and then this is Ba1, and these concentrations were different, there'd be no way of telling. You might be able to tell, but it'd be really tough. But if we have these concentrations the same, these ratios are the same, you can just look at the KSPs and tell what order. So I'm going to prove this right now. Because the other thing that I ask, it says, what is the concentration of selenide needed to begin precipitation? And it says, solid K2SE is slowly added. The solid is important because if I took potassium selenide solution, which is very soluble, and poured it in, we're mixing, which means every time I poured in a little bit more of the solution, we'd have to figure out the new volume, find out the moles, divide by the moles. But what we're saying here is if we put in solid, just these little dust of this stuff, it doesn't change the volume. So that's a very important thing. If we put in the solution to that, then every time we added in 1 mil, that would change the volume and change the concentration. We'd have to do the same stuff we just did for the precipitation. We'd have to do that volume times the concentration, figure out the moles, divide by the new volume. We'd have to do it every single step, and it would be horrible, or maybe hilarious. But in this case, we don't have to. It doesn't worry us because we put in this tiny bit of solid. These are really small numbers, so we don't have to put in that much solid anyway. And it's not going to change the volume. If it does, it's going to change it by like 0.0001%. We would never notice it. So that's the importance here. But what's also going in, the thing that's important is this selenide. That's going in, and it's going to react with the magnesium, calcium, and barium, in turn, creating these insoluble salts that are going to fall out. Okay. So it's the selenide that we're interested in, and here are the 3 reactions. So we have magnesium. See if we can't fit it all on this board. So we're going to use this, and we're going to use that the QC is equal to KSP when the reaction just starts to precipitate. And then we have the other. So you have to write out the KSP expressions for each of these things that are going to precipitate out, because we're going to be using those. And then we have the barium. Solid. And I'm trying not to jump ahead here, so it might seem a little, we have to do these because we have our KSPs, but exactly why we're doing it might not be quite clear yet, but that's okay. So what we do know is that the magnesium concentration times the selenide concentration is going to be equal to what? What number? Yeah, right up here. So it's going to be 8.31 times 10 to the minus 4. So this one is going to be the concentration of the calcium selenide. It's equal to 1.15 times 10 to the minus 11. Barium selenide. It's going to be 2.55 times 10 to the minus 7. Okay. So those are the expressions that we're going to use. Now the question is, let's see, here. So actually, let me put the list here. So what is the concentration of the selenide for each metal ion What is the selenide concentration for each metal ion when it begins to fall out of solution? In other words, when QC equals KSP. We know when QC equals KSP, it hasn't fallen out, but it's ready to go. So since that's what we're looking for, we can just use the KSPs here. So what we say is that the selenide, we want to know this, selenide concentration we want to know, if we put in the concentration of the magnesium, which we know, we want to know what selenide is. So this is going to be 8.31 times 10 to the minus 4 over 0.14. Okay, and this comes up to be 8.31, 10 to the minus 4, divided by 0.14. So we're adding the selenide in, and it goes from 0 molar to like 10 to the minus 12, 10 to the minus 10, 10 to the minus 8, 10 to the minus 5. When we get the selenide concentration up to 10 to the minus 3, 5.94 times 10 to the minus 3, magnesium begins to precipitate out. That's what this means. So this is answering that question for magnesium. Then we do it for each in turn. Same way. I'm going to do all the nitty-gritty stuff here. Make sure you see every step. So we'll take a little longer. 1.15 times 10 to the minus 11 divided by 0.14. So when we want to precipitate out calcium, we need to get the selenide concentration up to here. So to get the calcium to fall out, doesn't take as much selenide as the magnesium. And then we do the last one here. .55, and then this is going to be 1.82 times 10 to the minus 6 molar. Okay. All right, so we're saying we know that when these two together, multiplied together, equal this, that's when the precipitation starts. Well, we know what magnesium is, so we had to figure out selenide. So when selenide equals this, times 0.14, it equals this, means the precipitation begins. So looking at these numbers, we start with selenide at 0 molar, and minus 20 molar, 10 to the minus 15. When we get, which one of these ions is going to fall out first? Yeah, we're starting from 0, and this is the smallest number. So this falls out first. Then next, so as this starts to fall out, we keep over, I say, well, isn't the selenide being used up? It is, it's precipitating out, but we can keep up easily. We just keep pouring more of that dust in there. And then we finally reach this point, this starts falling out. And then we have to go way up to here. This is still pretty small, but compared to these, we don't have to, we have a lot further to go. And then this is 3. Let's see. Calcium, 1, 1. Barium 2, magnesium 3. So from this I knew that was the case, and it's a nice thing to know where you're going, but this proves it, and this shows you what you need to do. Okay, so that's the first step. So what is the selenide concentration for each? What is the order of What is the order of the ions to precipitate? That is here. And you just found it here again. So we've answered that question. Okay, and then the last 2 things. All right, so those answers are over here. And then when the second ion begins to precipitate, what percentage of the first ion is left in solution? So we know that the first ion, so we start adding in the selenide, the first ion starts to precipitate out. As we keep adding more selenide, the first one keeps precipitating out, keeps going, and then finally the second one is about to precipitate out. How much of the first one is left? Is it all gone? Is 99% of it left? This will tell us. And then when the third ion begins to precipitate, what percent of the first 2 ions are left in solution? So this one actually takes almost as long to write out the question as to do the answer here. Okay, so this starts precipitating out first. This is going and going. When we reach this concentration, this guy starts to fall out. Well, since they're both in the solution together, all we do is we take this concentration and we put it here and figure out how much calcium is left. When we do the next one, when this starts to fall out, we take this concentration and we put it here and we put it here. So that's what we'll do. So we can say this. And now we know what the first thing is. So when calcium begins to precipitate, barium begins to precipitate, the concentration of the selenide is here. That's what that number means. That's what we found. So put this in the calciumic equation. One point. I have a habit of mixing those numbers up right there. So we want to do that right. Well, when the barium starts to precipitate out, this was 0.14? This can't be 0.14 anymore because it's been precipitating all this time. So this is something different now. So we write it as this. And we put in the value that we have when barium begins to precipitate out, which is 1.82 times 10 to the minus 6. So let's see what we have. It should be less than 0.14. It has to be. Can't be any more than that. But we'd expect that it would be very much lower because we had to go way up here to the next one. So this is, yeah, it is not 5. That was an old man slip there. Need the larger calculator. larger geriatric calculator. That's the concentration of calcium now, when the second one falls out. So we need to find the percent of calcium. That's going to be 6.32. That's the part of it that's left. What was the total concentration? What did we start with? Make sure we're on the same page here. What did we, before we began doing anything here, what was it? Yep, that's what we started with. It was 0.14, and then you just multiply by 100%. So for these ones, you'll always go back to the original, whatever it is. It won't necessarily be 0.14, it could be 0.2, whatever it is. But you go back to the beginning. This is what's left in the solution. What it started with was 0.14 times 100%, and we end up with 4.51 times 10 to the minus 3%. Minuscule. Now that should be good enough, but you might have a precipitation, you might be trying to separate these out and say, that's not good enough. It's hard to imagine somebody having a problem with that. That's nothing. But if this had come up to be like 25%, you might say, no, you can't do this reaction. That just has not separated them out enough. And then the last one, when the last ion, since we know what it is now, we'll call it, let's say it's magnesium. When magnesium begins to precipitate, the selenide concentration is there, 5.94 times 10 to the minus 3. Okay? Put this into the calcium and barium equations. Let's see what we have. First thing we should have is calcium should now be much smaller than this because we've added in so much more, and barium should be less than 0.14. So we have this, we put in calcium. I'm going to do them right next to each other. Nope, that's not it. That's why I mix these up a lot. You see they're pretty close. So, that's what I'm after. 2.55 times 10 to the minus. If it was on one sheet, it would be a lot easier, but it's on the wall. So we have this, and so we say calcium is going to be 1.15 times 10 to the minus 11 over the selenide. Barium is going to be analogous. It's going to be its KSP over the concentration of selenide. And it's that selenide when the magnesium starts to fall out. So this is going to be 1.15 times 10 to the minus 11. Selenide, what did I say? Where is it? Oh, here. And this is going to be 2.55 times 10 to the minus 7. So just doing that same calculation we did, but just the two of them this time. So 1.15, 11, divided by 5.94. Molar, and then this is 2.55, 5.94, and this comes up to be 4.29 times 10 to the minus 5 molar. And then the last thing is the percent calcium is 1.94 times 10 to the minus 9 over 0.14. Percent barium is 4.29 times 10 to the minus 5 over 0.14. That's why I also keep it as the same number so that there's no confusion at the end. You don't have to look back. It's always going to be the same, times 100%. Now I'll go quickly through it again just to see and to show you everything that you need to know here. And then this is 1.39 times 10 to the minus 6%. So much lower than it was. And then this is 4.29 times 10 to the minus 5. And I get 0.0306%. So these ones are determined over there. Okay. So for what is the order of ions of precipitate? You just look at the KSPs. That gives you that answer. But if you want to know when they fall out, you just set up these expressions for each of the ions, and you're going to put in 0.14, 0.14. That tells you what the selenides are. So that one, that's pretty straightforward. Usually everyone gets this without too much trouble. Then, now this is tricky, and I'm not going to, if you're feeling like this is overwhelming, it is. It's a pretty, this is a real life calculation. This is something that has to be done when people are dealing with these kinds of reactions. But it says when the second ion begins to precipitate out, this is when the selenide concentration has been rising from 0. It's rising up. It hit this one first, started to precipitate that. When it reaches here, we want to know how much calcium is left. We take this value and put it into the calcium expression. We get here, divide by 0.14 times 100%. The selenide concentration keeps rising. When it gets to this point, the magnesium starts to fall out. But we say, well, we put these into the other two ions. We solve it the same way. So that'll be a good one to go through and I have a video lecture on that. Shows everything that you need to know there. But yeah, don't get too freaked out with this one. But it's worth a lot of points. You want to make sure that you can do it. And you can see that if you do this one, or you look at the video lecture that I did, it's going to look exactly the same way, just different numbers. It's very, very procedural. All right, so we'll stop there. We'll do the KF and KD stuff on Monday. Let me tell you what will not be on the exam later on in the chapter. That's the last monster problem that we have. Okay. Okay, so we have the complex ion formation. That's in 17.5. We're going to do that one. But then 17.6 and 17.7 won't be on the exam. So that's the complex ion solubility one. There's two fairly large problems to do there. We won't be concerned with those, and we won't be doing qualitative analysis. So this will be, we'll do a KF and KD problem, it's called. Formation constant problem, that'll be the last one. It's fairly straightforward. So that one will probably take about 15 minutes on Monday, and that'll be the last calculation. So if you're doing stuff out and you're unsure, the exam guide, well, actually I'd probably put those in there. So let me say which ones we don't have. So what you are not responsible for here is 32. And what we got here? And 31. 30 is going to be, that's the KF problem. You have to do that one. But 31 and 32, we won't have a problem like that. And then 25, we won't have a problem like that. And everything else is on there. So use that as a guide. But if you're in doubt about anything, let me know. All right, I'm going to do the calculations for the lab. And then after that, if you want to see, anyone wants to stick around and do more of this stuff, I know. I see it on your faces. This is as thrilling for you as it is for me. I dig this stuff. This is pretty neat. You can get this done. Pretty slick. Yeah, there's a lot going on there, but it is something that follows the same rules each time. So we'll do I'll do the calculations here. Then I'll do whatever. If you're all set, you're all set. You're not going to hurt my feelings. There's no doubt that I bought a box of Hostess cupcakes. And being 50, that's a bad idea, but it's like calling me. I say, are they really as bad as I remember? Are they? I'll give them a try. But that will be my dinner. But I'll stick around as long as you want me to. So if you're set, I would definitely take a picture of this, get this, and but if you're set, you can have a good rest of the day. If you want me to do the calculations, I'll do those in a moment. And then after that, I'll do any problems that you like. So stick around for anything you like. And I'm going to get some water. So just relax for a moment here. Never happened. Footprints in the sand kind of thing. God. Yeah. A few billion years, the sun will burn out, and then it'll be gone. Galaxies will spin into the black holes at the center. Various other things, but well, we have some work to do before then. All right, so now we'll just look at each of these in turn. So the sodium hydroxide, we know we can't find the concentration directly because it absorbs water. But potassium hydrogen phthalate, that's a whole different story. It will absorb water, but once we heat it up in the oven, desiccate it, we know exactly its mass, which means we know its moles, and we know the reaction is this. The big thing is that it's 1-to-1. So for every mole of this that reacts, 1 mole of this reacts. If we know how many, what our volume of sodium hydroxide was, then we can find the concentration. So here's what we do. I'll just use my values here. I'm just kind of basing them off of things that I saw. So 0.24 grams of KHP. So everyone will have their own. Different. No. Okay, so this will be 204 here. This is 1 mole of KHP. If you look at the reaction, 1 mole of KHP will react with 1 mole of NaOH. That. So your value goes here, everything else will be the same. Oops. So this comes up to be 1.18 times 10 to the minus 3 for me. I'd imagine yours will be something similar, probably the same order of magnitude. And then the concentration of the NaOH, which is what we're after, right? Oh, yeah. On the wrong page here. Yeah, so so the moles I realize for the calculations I want the moles of KHP, so this is where you'd stop for that, but then you can see they're the same. So it says moles of KHP, so I'd have to put in this value at the top here. But what you do is you take this value, which is the same number, because it's 1-to-1, and then you divide by your volume. And my volume was 10.75 mils from the result sheet. And I saw people had pretty much the same, around 10 is what you had, right? So whatever you get, if you probably, I saw between like 9 and 11. So whatever it is, just change to liters. Make sure you don't forget to do that. And my value, which is the exact value. I hope you get close to mine. I just made these up, so. But I'm guessing that you're going to get somewhere around 0.1, maybe 0.09 something. So that's your sodium hydroxide. You got to do it 3 times and take the average, or however I set it up here, what I say to do. Yeah, so you can find the concentrations for each run and then take the average. Okay, so that makes sense. All right, so you're going to do three of those and average them. And then we have to do so now that we know the concentration of the sodium hydroxide, we can determine the concentration of the other ones as well. So I should say for the acids, so we got, what's the next one here? We do, so So this is HCl titrated with NaOH. Okay. So we're going to be using this value. You'll be using your average. So we have that concentration. So we take, for me, I'm going to take 0.110 moles per liter times the volume of that I used for the HCl titrated with NaOH. And from mine, it was 11.93. And that's going to give us moles of NaOH, which will be equal to the moles of HCl. Because the reaction was this. All of this is 1-to-1. Don't have diprotic acids or anything we have to worry about. This is actually complete. So, so we'll do this out. I get 0.11 times 0.01193, and this comes up to be 0.00131 moles of sodium hydroxide. According to the reaction, I'm going to write this out here. There's no problem. I'll show you. Let me just do this out here. We all know it's 1-to-1 here, so we know that these numbers are going to come up to be the same. So if you just wanted to do this, use that arrow to indicate you did some work, but it was work that wasn't worth even mentioning, and you just put that there. I'll understand that. That's acceptable. I'm just showing you what happens here. We're using the coefficients from here to find that these are indeed equal when we knew that they must be. Okay, and then the concentration of the HCl. Put this up a little higher. Concentration of the HCl is going to be the moles divided by the volume of the HCl that was used. What was that? Is that 10 mils? Did 10 mils used? Yeah. So that one, we know that one. So everyone's going to have this value here. You pipetted the 10 mils in. And I get 0.131 molar HCl. And you'll do that the 3 times to get your average. Okay. Now the acetic acid works the exact same way. I'll just do it up to just be complete. But the acetic acid is also a monoprotic. It's weak, but it's a monoprotic acid, so it's going to have the same stoichiometry. So everything's going to work exactly the same way. But let's be complete. And you can see that all that's changed is that acetate group. This part here, but everything else looks the same. So I use this 0.1 because we titrated it with sodium hydroxide, so I use the concentration again. And for this one, I had 10.17 mils, so this becomes this. So the acetic acid and the HCl don't necessarily have the same concentration. They should be different. So we should use different amounts here. And this is 0.00112 moles of sodium hydroxide, which must be equal to the same number of moles of acetic acid. And you're very free to do that. Just say that you can even make this equal, but that seems to indicate that these are the same thing. But if you put this kind of proportional arrow here that says something happened, and we found that was true. Okay, but we're all aware of what that is. And then the concentration of the acetic acid is going to be 0.00112 moles over the volume of acetic acid used, which I assume is 10. I don't think I changed that. And so this becomes 0.112 molar. Yeah, I think for that. It's good, yeah.
The 0.01017, what value
this was the volume of the sodium hydroxide needed to titrate the acetic acid. So yours will be different, most likely. Just be by chance that they be the same. So you look at your results sheet for that part of the titration. Okay, and then the last one is the HCl titrated with the with the ammonia. So this one works a little differently because the thing that was in usually what's in the burette is standardized. What's in the beaker is the thing that's unknown. But in this case, we know what it is. So what you do, so for this one, so what we're going to do this time is we're going to take the volume of the HCl times the concentration that we know. That's going to give us moles of HCl. And write the reaction. So this is just slightly different, but the stoichiometry, everything's the same. It's 1-to-1. But this time, what you're going to do is you're going to take the 10 mils of this times the concentration to get the moles. That's the moles of ammonia, and then you divide by the what you titrated with the ammonia. In my case, it's 9.54. Okay, so what you do is, you're going to take this, we're using this value here. So we do that because if you had the HCl in the burette, then the flask will contain the ammonia, which will be pink, because you'll put the indicator in there. And as the color fades away, you can watch that too. That's called a back titration, but it's tougher to see. No, there's no problem doing it. It's just it's easier to have the base in there. So we have, this is going to be 0.1, this is mine, so whatever you have, times the volume that was in that beaker, which was 10 mils. So this becomes 0.00131 moles of HCl, which must be the same number of moles of the ammonia, because it's 1-to-1. So the concentration of the ammonia then is going to be 0.00131 moles divided by the volume of ammonia you put in. So this one won't be 10, unless it's just by chance. For mine, I have it as 9.54 mils, so 0.00954 liters. So this is the only one where we've done everything, and the last thing we divide by 0.01 for these last two, but here we're dividing by what was taken out of the burette. So it's backwards, but just made it easier to see the color change. So 0.00131 divided by 0.00954, and this is going to be 0.137 molar. Okay, no guarantee my numbers anywhere near close, or they're going to be anywhere near yours. I just took the numbers that I could remember as people were showing me the numbers they had. And these are what we normally see. It's usually around 0.1. So these are the concentrations you'll have when we do the lab next time. So all those bottles that are on the back up behind the whiteboard, you now know the concentrations. Any questions, concerns? So make sure you get those. You'll have to do 3 calculations of each of these and then find the average that I did. But yeah, so you've got 3 times as much work, but you can see it's not too bad. A little bit repetitive, but shouldn't be too difficult to figure out everything out here.
Good luck with today's lesson.